Good morning. Okay, good morning, everyone. So today's topic is again structured graphical models such as Bayesian networks and Markov networks. And we're in the middle of this topic, and we will focus today on an important topic, which is called sampling. That is, once we have constructed a graphical model, how do we extract samples from it? So we will look at specific methods. One referred to as ancestral sampling, which is used when the graphical model is a directed graphical model, also known as Bayesian networks. And then we will discuss another sampling method called as Gibbs sampling, which is the method of sampling from an undirected graphical model. So that's the main topic for today, is sampling. And we'll look at examples of Gibbs sampling from a normal distribution or a Gaussian distribution. And we'll look at Gibbs sampling from a machine called restricted Boltzmann machine. How do we get samples from that? So so that's the part about sampling. And then we'll talk a little bit more generally about the advantages obtained by viewing the deep learning model as a graphical model. And then also at the topic of learning about dependencies in a set of data so we can construct these models appropriately. Okay, so let's begin. Let me put up the first set of slides.
Bayesian network is one of the primitive one undirected models, undirected, directed, undirected.
Okay, there was some extraneous noise which we got rid of. Okay, so I was about to begin with my slides for the day, and this is about sampling from graphical models. Okay, so the place of sampling from graphical models within structured probabilistic graphical models is we had finished an overview. We talked about the challenges of unstructured modeling, that is the data of various types, and using graphs to describe model structure. We talked about directed graphs and undirected graphs. So today we are into sampling from graphical models, and we'll also do 3, 4, 5, which is advantages of structured modeling and learning about dependencies. And we'll be wrapping up this topic in the next lecture. So we'll cover the middle part of the lecture of this topic today. So within topics in sampling from graphical models, we'll look at sampling from directed models. Directed models, if you recall, are also known as Bayesian networks. And ancestral sampling is a method appropriate for Bayesian networks. We do what's called as topological ordering of the nodes of the Bayesian network, and we systematically proceed from lower number nodes to higher number nodes, and each time obtaining a sample from the appropriate conditional probability distribution. Sampling from undirected models is quite different, and there are several methods for these. Several of these are known as MCMC or Markov chain Monte Carlo methods, most famous of which is Gibbs sampling. And we will illustrate it by showing how you sample from a normal distribution using Gibbs sampling, and how you sample from a restricted Boltzmann machine using Gibbs sampling. And we discussed that these Gibbs sampling methods require a time for them to settle down. The earlier samples may not be as good as the later samples. Okay, so we begin by looking at sampling from Bayesian networks. So when you construct a graphical model, saying here are nodes and edges, they facilitate drawing samples from a model. Bayesian networks directly are appropriate for a procedure called ancestral sampling. And that's a fairly simple method to describe. And here I have below two Bayesian networks. I have here X1, X2, X3. These are the parent nodes, and then we have the child nodes, Y1, Y2, Y3, Y4. And the arrows indicate the directionality. So we'd order these nodes in some way, and then we number them as 1, 2, 3, 4, 5, 6, 7, 8, like that. And we use those nodes, and we got to start with nodes that are in a non-cyclic way. So in this particular graph, we have a peculiar situation that is a cyclic graph. So this is not quite a directed acyclic graph. There is a cycle over here. So this is not appropriate for a graph like this. Whereas this one is a directed acyclic graph. We have something describing a car situation, battery age influences battery dead or not, and alternator influences no charging, and fan bell broken, no charging, and so on. So this is a particular network. It's a true Bayesian network or a directed graphical model. So the sampling is possible only here, which is a proper Bayesian network. So we'll see how one can have a sample of the data. So we got all of these variables: battery age, alternator broken, fan belt broken, so on. All of these have a certain sample in it. In the sense, a setting for each of these variables. Battery age is new or old, or exact number of years, and so on. So when we assign values to all of these variables, for all of the variables, we have a sample of that distribution. So ancestral sampling says sort the variables xi in the graph into a topological ordering, so that for all I and j, j is greater than I if xi is a parent of xj. So here we have a proper directed acyclic graph where we have xn is the parent, x1 is the parent of x2 and x4, x2 is the parent of x4, x4 and x2 are parents of x3, and x3 is the parent of x5. So it says sort these variables such that for all I and j, j is greater than I if xi is a parent of aj. This has already been sorted in the numbering scheme. This is 1, 2, 3, 4, 5. The numbering you see here is the topological sorting of these variables. And we generate the first sample from the ancestor that comes first, right? X1 is the ancestor that comes first. So we sample X1 from the distribution probability of X1. Remember, this is a Bayesian network, so we are given all the conditional probability distributions of all the variables. So we'd be given the probabilities associated with values of X1, and we would be given the conditional probability of X2 given X1, with all the values for X1 given for each value of X2 there is. Similarly for X3, for each value of X3, we would have values for the probabilities associated with every setting of the variables x2 and x4, which are parents of x3, and for every setting of x3 as well. So we know all these CPDs, or conditional probability distributions. To generate one sample, we sample from x1, we sample x2 from x2 given x1, and we sample next from x4 given x1 and x2, because we already have no set of values for x1 and x2. And similarly for x3 given x2 and x4, and then finally x5 given x3. So once we have a value for each of these variables, then we say there is a sample. So if each conditional xi given PA stands for parent in the graph G, xi is easy to sample, then the whole model is easy to sample. So we have some type of a network that has learned the probability distribution, and if we want a sample, we can get it. Then you can ask the question, why do we need a sample? One is, of course, in some practical situations where we want to generate an example of an audio or example of a video, example of an image. Those are some things. But also, sampling turns out to be an extremely important approximate method of inference. So if you have a set of variables and we want to infer the value of some variable down the line, given some values, then you can use sampling to generate enough samples and to take an average of them to calculate a probability. So the role of topological sorting is that it guarantees that we can read the conditional distribution in this equation. This equation is P of x is equal to product of Pxi given parents of xi. So that is just a product of all the conditional distributions represented in the graph. And that product is a factorization of the joint probability distribution. And we are able to sample them in order by having a topological sort. Without topological sorting, we might attempt to sample a variable before its parents are available. So we can state ancestral sampling algorithm as start with the lowest numbered nodes, draw a sample from the distribution Px1, which we call x1 hat, work through each of the nodes in order. For node n, we draw a sample from conditional distribution Pxn given parent of n, because we know the parents, where parent values are set to their sampled values. Once final variable xk is sampled, we have achieved the objective of obtaining a single sample from the joint distribution. And supposing we say, well, we don't need a sample from the entire distribution. We want a distribution, a marginal distribution of one variable or two variables or three variables. For example, if you want to draw a sample from the joint distribution of x2 and x4, we simply sample from the full distribution, retain just the values of x2 prime and x4 prime, and discard the remaining values of x hat, j not equal to 2, 4. So this is a method that's pretty good for generating a sample from the entire distribution or from a small set of variables from that distribution. Okay, let's then compare this to sampling from an undirected graphical model. Ancestral sampling applies only to Bayesian networks or the directed graphical models, and we can sample from Markov networks by converting them to Bayesian networks. We saw earlier on that a Markov network or an undirected graph can be converted into a directed graphical model, and by using some algorithms, one direction of which is moralization. That is actually goes from directed to undirected graphs. And so we can use some methods for converting them. But it also solves intractable inference problems to determine marginal for root nodes of the directed graph. So this involves intractable inference problems by converting them from Markov networks to Bayesian networks. It's not practical. So or introducing so many edges that the resulting directed model becomes intractable. So drawing samples from a Markov network is an expensive multipass process. Okay, so this says it's not so simple with Markov networks. You can't simply convert them into a Bayesian network. It's an intractable problem. So we need a better method. And the solution is going to be Gibbs sampling. Gibbs sampling, same Gibbs. Gibbs keeps appearing a few times in machine learning. We've seen Gibbs when we talked about, in the case of a Markov network, we talked about a Gibbs distribution, which involves a partition function. And then we have an unnormalized distribution, which is obtained from the factors of the distribution. So Gibbs sampling is not exactly the same thing, but it can be used with the Markov network, but it's a sampling method. So it's the simplest approach for sampling from a Markov network. We assume that we have a Markov network over an n-dimensional vector of random variables x. So we have n random variables over which we have defined a Markov network. So this says visit each variable x sub I, the ith variable. Draw a sample conditioned from all other variables. So assume that you are able to draw a sample from one of the variables given all the others. Really, how can you do that? Well, you can say, what if we had one sample from the entire distribution of all the variables? It says, okay, keep all of them fixed, and then choose the ith variable from which you want to sample. Now you have all the other variables fixed. So this is saying I can draw from this distribution given all the others, which means there are a few variables that we have to deal with. And as long as you know that distribution, a Markov blanket allows you to ignore all the variables. So you can actually generate a sample. Due to separation properties of Markov networks, we can equivalently condition on only the neighbors of xi. That's why we're talking about the separation properties of Markov networks. Supposing we had an original joint distribution of PFAB given like this, and then this says you start with some arbitrary point and you fix the values for that particular sample, and then you fix one value and you sample from the other one using the conditional distribution. So this kind of shows all the paths that one would take. This middle picture shows the paths one would take to obtain Gibbs samples, and on the right hand side shows some samples from the distribution, which looks pretty good. They look like the original distribution. The green points here look like the blue points. These are samples from the distribution.
Hello, sir.
Yes.
Sorry for interruption, but so we are not be able to see the screen.
Yes. Okay. Thank you for pointing that out. I need to go back to my settings, and I need to share screen again, which is okay. You're okay now?
Yes, sir.
Okay, very good, very good. Okay, that was very critical. My previous slide, I was pointing out a slide which showed samples obtained from the Gibbs distribution. On the left side, we had samples which were from the true distribution. In the middle, it shows how we go from one sample to the next sample to the next sample. This is a method called Markov chain Monte Carlo method to generate samples, and it's showing how we get the next point and so on. And the final set of samples are all shown on the right hand side. And this is being accomplished by using Gibbs sampling here. This is the algorithm for Gibbs sampling with m variables. We initialize the first sample, zi equal to 1 through m. And for t equal to 1 through capital T, T is the number of samples. It says sample the first variable at time t plus 1. See, we are given one sample already. So that's at time t, let's say. And at time t plus 1, we sample from that one variable given all the others. So we need to have access to that conditional distribution given all the other variables. And similarly, you fix that value z1 now. And then in the second step, we sample from z2 given all this. See, in this case, z1 is t plus 1, the rest are all t. And we are sampling from z2 given all of that. So we obtain samples like that for all the variables. When we come to the end, there are m variables here. And so we would have one sample of all the m variables. So Gibbs sampling says, start with a sample. You got to have some sample to begin with. And then you simply start going through all the variables one at a time. and generate a sample from that. So this is being illustrated here again for a Gaussian distribution, which says that you would start with some sample. It says the samples are being obtained here in some way. At t equal to 0, we have a sample over here. And then we fix that value along x1 and we sample along x2. So we go up like that. And we fix that, we come down like that. And then we fix that, we come down like this. So it's always going in the x1 and x2 direction. We're changing the sample, changing the sample. So as we go along, it is just moving up or down or left or right. And that way ending up covering the entire space. And as soon as we get a second variable, after we know the first one, we get a new sample. So this is how Gibbs sampling works, and the entire distribution ends up looking like the true distribution. And anyway, that's how Gibbs sampling works. This next one is Gibbs sampling applied to a deep learning network. In this case, it happens to be a simple deep learning network. It is a restricted Boltzmann machine, an RBM, which consists of visible units V and hidden units H. There's connections between V and H only. So we say that this RBM represents a probability distribution for any values Vi and Hi. The probability is given by probability Vi Hi given the set of weights W is exponential Vi W Hi, and the denominator is the partition function here. That's the normalization term. So this says given the weights V, H, and W, we are able to obtain the distribution associated for any given setting. So this is what a restricted Boltzmann machine represents. And here is an example of a restricted Boltzmann machine where we have the VIs, the value here, and then these are the HIs, the values here. And this is for a particular setting. I guess this is an MNIST handwritten digit, and which has got a certain set of values here, and there is a hidden values here. So this setting, we can ask the question, what's the probability associated with this setting? And that is obtained by the formula given up here. And that is how we calculate. So this represents a probability associated with this particular input because it has a given set of settings here, Vi and Hi. For a given W, that's important to say that. So how do we sample from this? It says the conditional probability P of Vi equal to 1 H given H. So we need the conditional probability. So Vi given H. And then similarly, Hi equal to 1 given V. So these are the conditional probabilities that have got a fairly simple formulation. As long as you know the W's and you know the value of H, you can calculate the probability of Vi. Similarly for H also. So as long as you know what the conditional distributions are, you can sample from them. And using Gibbs sampling, we can sample from joint probability V, H given W. It says use Gibbs sampling and it will give you a certain sample of V values and H values. Then we ask the question, well, we're only interested in, let's say, a sample like a handwritten digit. Give me a handwritten digit that you have learned. So it says, well, you just generate a sample of V and H, sample from the distribution VH. It gives you a sample V infinity, H infinity as shown here after it's been trained and it has settled down. That's where the infinity comes from. So the particular example, V in that case, represents a digit. So this neural network can be sampled to say, give me a digit. So it will start generating 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, based on the distributions that it has learned, and it generates these kinds of samples. That's exactly what is shown over here. Final states after 1000 Gibbs sampling steps is showing you all the 7, 2, 1, 0, 4, 1, 4, etc., etc. So it is showing these after a certain number of steps. I suppose this is somewhat happening in the earlier part of the training, but these are the examples that this restricted Boltzmann machine is able to generate. So you see from here the powerful situation where you are inputting a set of training samples, going through the visible nodes into hidden nodes, and we're using a particular network called the restricted Boltzmann machine, which has learned the values W through backpropagation. Once it has learned it, you can now ask it to generate sample. This is just like a human brain. After a person has learned about, let's say, handwritten digits, and you're asking, give me some samples, and you can now draw any number you want, roughly from that distribution. What about the case of Bayesian networks, and can Gibbs sampling be used? And the answer is yes. Gibbs sampling is not only useful for Markov networks where there is no directionality. You can also use it for directed graphical models. We saw this example of Alice, Bob, and Carol earlier on, the relay race. It's a directed graphical model. And we can generate samples from this. That is, give me a sample of the time Alice finished, at the time Bob finished, the time Carol finished. One example. All right. So as long as it knows what the conditional distributions are, you can generate those samples. In this simple case, they are simply written as values that belong to 0, 1. So this is a very trivial example where it has value 0, 1, 0, 1, and 0, 1 here. And so at time t equal to 0, we initialize a particular sample. It's a 1, 1, 1. And this is generating the next sample, which is a conditional distribution for Bob, and given Alice and Carol, which generates Bob, and similarly Carol, and then you keep on repeating it. So these particular value that you get out after you have done some repeated number of rounds here, you get a sample, and that sample would come from this distribution. I think a little bit more interesting distribution would be values between 0 and 1, and not exactly 0 and 1. I guess it is. This is actually curly brackets, which means it's a value between 0 and 1, between 0 and 1, between 0 and 1. It is not 0 or 1. So it is more interesting than that. So it is giving you value between these three. Like this could say that's 0.5, 0.8, 0.9, something like that would be a sample from that distribution. Of course, it all depends on the conditional probabilities that you need to know. The CPDs have to be known. Bob given Alice has to be known. So given that, you can generate samples. So that's Gibbs sampling. So something to keep in mind that Gibbs sampling termination, after one pass through the graphical model and a sample of n variables, we still do not have a fair sample. So if you say, well, here is a sample, we just went through all the variables from one to the last in topological sorting, or in this case, in Gibbs sampling, you have generated one sample. It doesn't mean it's a fair sample, that it's a reflective of the true distribution. Instead, we must repeat the process and resample all n variables using the updated values of the neighbor. This says you must keep on doing this for a while. Asymptotically, after many repetitions, process converges to sampling from correct distribution. The reason here is you might have started with a unrepresentative sample, in which case you're going to be generating samples that are not truly reflective of all the variables. So it says you must keep sampling, and only after a while will it settle down. But the last point is saying here is difficult to determine when the samples have reached a sufficiently accurate approximation. There is a caveat here that says, should I get 5 samples or should I get 100 samples before I'm sure? This says there is an issue here that you may have to go for a while before you get a good sample. And I give an example next, which shows how in any MCMC or a Markov chain Monte Carlo sampling algorithm, the samples in the beginning are not as good as the samples later on. This is from a paper that I just came across, which talks about a method better than some methods such as generative adversarial networks, which are also methods for generating samples. This is based on the energy-based model. We just saw what an energy-based model is, which is just a Markov network where we're using a different formulation rather than simply factors. In an energy-based formulation, they have learned a model and they're using a version of MCMC sampling. Gibbs is just a one particular MCMC sampling method. They use a different variation of it called the metropolis adjusted Langevin, the Mahler sampling method, which obtained samples at the beginning of the chain. These are all the samples, all trained on celebrity faces. These are not real people. They're just samples that look like real people. And these are the samples in the beginning of the chain. But after you keep on sampling from it, it becomes more and more truly representative of the distribution. And the samples at the end look like this. And what's the difference between left set and the right set? Is that you see all kinds of little detail in the background, maybe in the face and so on, which are much more fine-grained and better samples than these samples on the left side, which seems to be somewhat blurry. And of course, they're not exactly the same sample. They're different samples, but this is kind of fine-grained. So this is about the need with Gibbs sampling to keep it running for a while and after a certain number of iterations. In this example, they said they generated samples after 100 iterations. So they went through 100 samples, and then beyond that, it got better. And they're saying the chain is smoothly walking on the image manifold and changing semantically meaningful and coherent aspects of the image. So you keep in mind here that if you go off of the original manifold, which is where all the samples are lying, and it becomes better and better. And when you go off the manifold, you get samples that are not truly reflective. So these are some interesting things to keep in mind. Okay, so I'm going to go on to the next set of slides. I think I need to share that as well. So this one is about the advantages of structured modeling in deep learning. Okay, so advantages of structured modeling in deep learning. Okay, so what do we get by using this graphical model way of looking at deep learning, right? Okay, so the topic is advantages of structured modeling. So what we get out by a probability distribution being modeled by means of a graphical model, we reduce the cost of representing the distribution. So we are not obtaining, for instance, we're not throwing a whole bunch of images of faces and say, learn the distribution. There are millions of pixels involved here. The distribution is impossibly large. The number of variables here and the number of values they can take, the number of samples you need, and so on. This says that's all being represented by this latent variable model. Like in this deep network here, we have the visible layer, then with the hidden layer, hidden layer, hidden layer, and so on. All of these are capturing the relationships between these variables. The correlation between variables is being captured. You can imagine what would happen if you assume all the pixels are all independent. You're going to get nonsensical images that don't look like faces at all. So you need some correlations between pixels. If one is skin tone, the next one is skin tone, and so on. Those relationships have to be maintained. And so that's all being modeled not by explicit correlations between the visible variables, but by implicitly by the latent variables. So we reduce the cost of representing the distributions as well as learning and inference. So once we have the network, if we want to infer a value, it's computationally more feasible in a network like this. And we can also sample in these kinds of models and so on. So this is a particular example of a deep belief network composed of what are called as restricted Boltzmann machines here. This layer, for instance, is an RBM here. And there's a name for this kind of a thing where we have We have directed models. It's called as a belief network, sigmoid belief network, sigmoid belief network. That's an RBM. All of these together are defining a graphical model which is representing some set of data, and the advantages we get, of course, are the reduced cost of representing distributions, and sampling is enabled. So what makes the advantages possible is that the operations use less runtime and memory. They don't model certain interactions and convey information by leaving edges out, because we are not using all possible edges between all variables. When there is no edge, the model assumes that we don't model a direct interaction. And it also does something called separating knowledge from learning, a less quantifiable benefit of using probabilistic graphical models. It allows us to explicitly separate representation of knowledge, learning of knowledge, or inference given existing knowledge. So we can learn the network, and then inference algorithms are quite different, and we can design those for the network. Learning is yet another situation where we learn the parameters. So these are three different topics in PGM, which are kind of distinct topics with probabilistic graphical models. So this says simply that the advantages are in terms of efficiency of representation, and also in terms of efficiency of sampling. Okay. Now, learning about dependencies is the next subtopic. They're kind of small subtopics, learning about dependencies. Okay. And okay, so this is the topic of learning about dependencies. This is similar to the topic of the causal models that we talked about earlier on. And this is viewing it from the point of view of probabilistic graphical models. So the subtopics here are that the latent variables reduce the number of needed parameters. And we also look at structure learning algorithms. How do we learn these? And then what are the advantages of fixed structures? So let me just summarize what these 3 points are first before we look at the slides. It says, supposing I wanted to represent a probability distribution of a large number of variables, such as a large number of photographs of celebrity faces. You would have to deal with very complicated interrelationships between these variables, the correlations between these variables, huge number of parameters. By saying I have a bunch of latent variables, we can reduce that dependency parameters by appropriately choosing these latent variables, which can be like the factors of influence. So it says there is a essential compaction going on by introducing latent variables. That's kind of interesting, that when you go from the real representation to an abstract representation, you are getting savings. This is like a human being learns about people. We don't remember about people by knowing pixel by pixel what their face look like. So it says we have some kind of an abstraction of these, and then abstraction of abstractions, abstraction of abstractions of abstractions, etc. All of that causes you to remember much more efficiently than if you had photographs stored of the face, which makes sense. That's exactly what a deep neural network is doing. It says those latent variables are actually allowing you to remember these things much more efficiently. So that's interesting. The second part is about structure learning algorithms. Okay, so what variables are causal, and what is the relationship between these variables? So there is a whole set of algorithms that one can look at, very complicated. We argue that these structure learning algorithms are actually sharply complete. Complexity wise, they're as complex as you can think of. If you have to look at all relationships and saying, what is the causality of it? First of all, we got to figure out correlations between variables, and then causality. This is an extremely complicated problem. And the third point we make on this slide, which is the point we make in this brief discussion, is that if you have a fixed structure rather than arbitrary structure that you're going to learn, you're going to, if you have no restrictions on what kind of a graphical model that you're going to be using, it's much, much more complicated than if you say, well, I have this structure where I have visible nodes and hidden nodes and hidden nodes and hidden nodes. We're fixing the structure. So that brings about a great computational advantage. So this is what this small vignette or something like that is about graphical models. Okay, so learning about dependencies. So a good generative model captures distribution over observed or visible variables V. So if you are going to have a generative model, what's a generative model again? Is a model that can be used to generate samples. And as I said, generating samples is an important task. Again, why is it important? To generate samples from the distribution, new samples you want to get. And if that's not important for you, it is also useful to do inference, which is if I want to go through the network to infer, given all this set, give me an answer. Who is it? Or what is the probability of this, and so on. Those are kinds of inference problems. And those are what generative models are used for. And it says a good model captures that distribution. Often the different elements of V are highly dependent on each other. So this is, any kind of image that you see has got dependencies that are very strong. The deep learning approach to capture these dependencies is to introduce several latent or hidden variables. Unlike standard graphical models where we say, here are all the variables, let's construct a graphical model, a Bayesian network for this or a Markov network for this. In deep learning, we say, we are going to be capturing all of this with a set of hidden variables, H. So deep learning captures dependencies in V by introducing several latent variables, H. Model can then capture dependencies between a pair of variables Vi and Vj indirectly. So the dependencies are no longer captured directly, saying what is the correlation between Vi and Vj? We don't ask such a question. So we don't explicitly saying how often these two values go up together, go down together. When goes up, will the other go down? So that's called correlation. Right? Today in this medical world, we're constantly talking about correlation and causality. In deep learning, we don't explicitly go about saying what is the correlation between these two variables. So we look at, instead of direct dependencies, we look at direct dependencies between Vi and H and direct dependencies between H and Vj. So we look at not dependencies between the Vi's themselves, but between Vi and H, between H and Vi. And this is what goes on here. That's what makes it quite distinct. It's like asking a network to figure out what are the relationships, which kind of makes sense for all kinds of medical data and so on. You're trying to figure out the relationships, correlations, and a deep learning method gives you a computationally feasible method. I got a simple diagram here, which tells you what is going on. What kind of efficiency can you get by having latent variables? And to illustrate that, let's take a simple case, V1 through Vd. D is the dimensionality of the space. So we have a set of visible nodes here, V1, V2 through Vd. And we have here a hidden node here, H. And together is a Bayesian network, you would agree, because it consists of nodes and edges, which are directed edges. So I can write the joint probability distribution of H and V by using simple Bayes rule as P of V comma H is equal to P of H times P of V given H, right? So this is the conditional distribution associated with H, and then these are all conditional ones V given H. So I can write this expression as P of H times product, where we're breaking it down into the specific VI. And what it really is saying is that these variables vi are independent given the latent variable h. So we're saying, we are not saying VIs are independent, but we are saying VI given H are independent, given that parent value. So this is the same kind of thing we talked about, as when you know a particular value, it doesn't matter about another value. So if you know this, what this feature is, then the dependency between these two is not important. So that's the modeling. So this is saying, I am not going to ask you to look at all the relationship between V1 and V2, V1 and V3, V1 and V4, V1 through VD. That's a large number of interactions. It's saying it's all going to be modeled by a hidden node VH that is going to capture all these relationships. And basically, we're saying we are given a set of hidden values, H1 and H2. There is some kind of a mapping that's mapping onto a manifold S here in the visual space, V1, V2, V3. So this is saying the data lie on some kind of a manifold. This is like looking at all the pixels of the faces. If you have millions of pixels, okay, every face is a point. But these points are not going to lie all over the million dimensional space because faces have certain similarities to each other. So they all lie on some manifold. And this particular set of hidden values are actually capturing, and there is some kind of an inherent function here that's capturing from these to this. This is like saying there is some kind of a mapping from the H's to these values, and those points lie over here. So that's the kind of embedding that is being captured. And it kind of gives you a sense of the efficiency associated by having latent variables. So this is the essential message here, that if you want to model a set of variables with tons of correlations between them, a very efficient way of doing it is not by brute force going about calculating all their dependencies by using standard correlations, but by constructing a deep learning model, which is makes it implicitly dependencies are being captured. So the computation savings by using H is that model of V without latent variables H will need a large number of parents per node in a Bayesian network, or a very large number of cliques in a Markov network. So you will need, if you don't use latent variables, they're all observed variables, you will need a very complex model. Just representing these interactions is costly, and they would require an exponential number of parameters. So this is simply saying, even if you have a set of binary variables, if all pixels can only be 1 or 0, the number of possible combinations will be 2 to the power of the number of variables you have. If you have 1,000 pixels, that's 2 to the power of 1,000 combinations. So that's exponential number of parameters. And a wealth of data would be needed to estimate the parameters, right? If the number of parameters itself is so large, the number of samples is maybe 10 times or 100 times that. So these are the kinds of savings that are possible. About structure learning, when searching for a PGM structure, that is, how do we get what is the structure of this network? If you're considering an arbitrary PGM structure, it is infeasible to connect all visible variables. If you say, look, I want to construct you're assuming that a Bayesian network is a good way to go, and you're saying, I'd like to construct the Bayesian network for my data set, then you would still have to consider all pairs of variables. And the way structure learning algorithms work is by performing greedy search, actually. So structure is proposed, model is trained, and scored. You would say, well, start about which are the most correlated variables in your data set. Let's draw a link between those two. And then once given that, let's look at another variable. So this is called as a greedy learning algorithm. And so this is, and then once you have a network, you say, how good is the score? And then you try another network, and you get a score for that network. And how do you get a score? Score is just the maximum likelihood over a given set of samples, which model gives it a higher probability, and you choose that network which maximizes the score. By using latent variables instead of adaptive structure, it avoids the need to perform discrete searches in multiple rounds of training. It says with latent variables, We don't have this greedy search and so on. We are completely bypassing all of this. So it says if you have a fixed structure, such as in a deep learning network, in a fixed structure, both visible and hidden variables are used, and they can both use direct interactions between visible hidden units to impose indirect interactions between visible units. And simple parameter learning techniques can be used to learn a model with a fixed learning structure, and it imputes the right structure on a marginal distribution. So look at the beauty of it. Deep learning is allowing you to model a distribution that you would have thrown up your hands and said, there are too many variables here. How do I get all the correlations? So what is actually a problem which is super exponential? The number of possible Bayesian networks for a given set of variables, if the number of variables is n, the number of possible networks is 2 to the power of 2 to the power of n. If exponential is bad enough, it is super exponential. But that's the number of networks possible. So it is a notoriously impossible problem to construct the most optimal Bayesian network for a problem. And instead, here we have a deep learning network that does this in a very elegant way. New variables H provide an alternative representation for V. And this is somewhat known to those of you who have done basic machine learning. Mixture of Gaussian's model learns a latent variable that corresponds to which category of examples the input is drawn from. So, so this says, it says if you learn, for instance, a mixture of Gaussians, if you learn that these are the components of the Gaussian, these are the probability of each of these Gaussians, you have learned a hidden variable which corresponds to the components. And it says once you know that, we have provided a model which can actually be used to perform classification between those modes, for instance, and it provides some additional information that that is also useful. Okay, I'm going to stop at this point. I believe it's the last slide. Yes. So I'm happy to take any questions on today's lecture. And again, summarizing in today's lecture, we looked at sampling. We looked at sampling from a directed model, which is called as ancestral sampling. We looked at sampling from an undirected model, famously the Gibbs sampling method. And Gibbs sampling, we looked at a specific example of sampling from a Gaussian distribution using Gibbs sampling, multivariate Gaussian. It's got to be at least 2 variables for Gibbs sampling. And then we looked at how it can be used to generate samples for a simple deep learning generative model called a restricted Boltzmann machine, how to sample from that. And then we looked at the termination criteria of Gibbs sampling, that an early sample may not be very reflective of the true distribution because you might have started in a wrong point. And so you have to wait for a while until it stabilizes and you start getting good samples. And then we saw what is the advantage of structured modeling. And a lot of it is computational, and the other is that you're able to generate samples in a reasonable way. Then we saw that standard structure learning algorithms have a serious computational problem in constructing Bayesian networks. And we are saying all of Bayesian network folks who try to construct graphical models to consider, well, can't I just model it using deep networks, which provide you a tremendous advantages computationally. Okay, so that's a summary of today's topic. And we'll have one last lecture where I'll spend a little bit time on how restricted Boltzmann machines are actually learned. We haven't talked about how do you learn that W and V and H and so on from a set of data. So that's the learning model for RBM, which if we understand, then we get a good sense for how unsupervised learning works in deep learning. Supervised learning is easy to follow. Unsupervised learning seems a little more challenging because there is no supervision signal, but we'll solve that mystery next time. Okay. All right. Do you have any more questions? Okay. If not, we will meet again on Monday. Have a nice rest of the week.